Right. Hi guys, my name is Sahil Shetty along with my teammates Joshua Ramayrat and Kiarash Behzad. The project topic that we have today is trajectory optimization and control of robotic arm. So the problem statement that we have is we're trying to optimize the motion for a robot arm and the motor control system. So the common problem that today um, robotic arms have is that it's not efficient enough while it travels from its initial point to its final point. The trajectory is not smooth. That is mainly because of the inverse kinematic problem. Most of these robots have closed form solutions because of their multi-degree of freedom systems.
Right. And these closed form solutions are very difficult to find. And that's where optimization comes in that it can help us find a solution through an iterative process. And so our project addresses that challenge as well as the challenge of controlling the motors themselves. In other words, once we've found the ideal thetas for each of the joint angles to reach a desired trajectory, the next challenge becomes controlling the actual motors on the arm itself such that when the motors are actuated, they stay at the thetas or the angles that we need them to be at so that they can reach the actual trajectory. And so moving on to the related work section.
Okay, so currently there are many existing approaches when it comes to optimization. These methods are used in different fields. Currently, we have many optimizers available and several algorithms which can be used in this project. We have mainly focused on just two algorithms.
Right. But the goals of all these algorithms, all these methods, is to find the global minimum or optimal solution to multivariable functions. And so, right, we do have a lot of options like particle swarm observation, which in genetic algorithms are neural networks. I can briefly describe what these do. So when you say you have a robot arm, and its movement, its motion is a multivariable function. So what that does is that it creates a multi-dimensional space that we either can or can't visualize. And so many of these methods, they start at certain points in that multi-dimensional space and they iterate on finding an optimal solution that kind of we set for ourselves. So particle swarm, particle swarm observation works by declaring multiple points and then having all those points try and find optimal solution. Genetic algorithms, it starts with initial conditions and then it finds a point or an optimal solution based off of certain criteria, certain fitness criteria. And then Sahil could.
Yeah, so talking about the interior point and the SQP method. So interior point, basically it's a class of algorithm wherein you can solve linear as well as non-linear convex optimization problems. When it comes to sequential quadratic programming or SQP methods, you can solve only non-linear constraint optimization problems. The main advantage of using the interior point is that the violation of any inequality constraint are prevented by augmenting the objective function. So, which is a common error that we face in the SQP method. Next
Okay.
slide.
So for our methodology of optimizing the motion of the robotic arm, we had the equations of motion pre-derived as well as the constraint and objective functions, which were all arbitrary because the goal of our project is not to derive these equations and functions. The goal is to test algorithms that can help us find solutions or optimal solutions to these functions and to these equations. And so what turned out to be the best method for our project was the direct collocation method. And this is another way of saying that we used sequential quadratic programming. And what I mean by this is that the direct collocation method is an umbrella term for the Runge-Kutta method, which is another umbrella term for Newton's method. So in other words, this is all numerical methods, numerical analysis. Okay, so moving on to the next slides for our results.
Okay, so for the approach and the results that we got, for this project, we are using two different models. and different methods in those models. The first model is the one for optimization, and the second one is for the control of links through state space. So in the optimization models, we tried designing a model which uses fmincon function and two different algorithms. The first one we used was sequential quadratic programming, and the second one was interior point. So for both of these for both of these algorithm types, we gave arbitrary input waveforms.
Okay, so here are some of the results that we got from the optimization algorithms. So here are the inputs that we got from the interior point optimization method. And they are indeed arbitrary, but they are the values that get us the angular positions and the angular velocities for the robot arm to reach the final point. And so moving on to the actual report, I just wanted to show some of the results for SVP. So the plots aren't overlaid, but let's just try and make sense of this. So x1, x3, and x5 represent angular position. x2, x4, and x6 represent angular velocity, all in radians. So this makes sense because angular velocity for x2 or link 1 starts at 0 and tries to settle back down to 0 when it hits the final point, which is time t at equal to 9 seconds. And then for x6, which is the angular velocity of link 3, it does start at 0, and then it does try and settle back down to 0 when it hits the final trajectory or final point.
In the second model in our project, we use the following model for the three-arm robot. And we use RFAT controller, as you can see in the right figure, which gives the three angles for each arm as an input. And it has got two feedbacks as the angular position and the angular velocity. So the RFAT controller to estimating the weight matrices for the dynamics of the robot, it's used Fourier series. And as you can see, we use two scenarios in 10 and 30 hertz. And you can see that the results, which the inputs are 45, 60, and 90 degrees. And as you can see, the results are converging pretty close to the input to the desired angles. So in an attempt to replace this Fourier series in the RFAT controller, we tried to use RNN to train the model to estimate the weight matrices to the dynamics of the robots. So you can see we used an RNN model with 10 layers, and you can see in the right-hand side the final actually Simulink model with the RNN and the controller and the robot itself. So to gather the training data, we use the following Simulink diagram to cover all the different scenarios. We use these three noise generators to create the input data, different input data. And as you can see in the plot, the final values they are converging to the desired location. But in the transition mode, in the first plot, in the first part of the plot, you can see that we have a lot of fluctuations. So we have to find a better way to gather the data. In order to do this, we use another model to fix this problem. We use 100 different set points between 0 and 90 degrees, and we gather all the information from the RFAT controller, and we added the result, the input and the outputs to the data that we gather from the noise generators. And as you can see, we still have the final values close to the desired location, but compared to the previous plot, in the transition mode, we have less fluctuation and we are very close to the desired one. And at last, the last plot, you can see we wanted to make sure that this happened in all the set points. So for the 50 set points, we ran it one time to the other, and you can see that we are getting the same good result in all the set points.